Welcome back. So at this point, you should have seen the program that draws a triangle, and you've run that. You have modified it to draw a square, and then you've also modified it to draw some other regular polygon, so a shape that has equal sides, equal length sides, and equal angles between sides. So you might be starting to see that there's actually a pattern in those programs, that really we're only changing a couple of things. Specifically, we changed our number of repeats, and we're changing our degrees. And as you look at the different programs, for example, to draw 5 sides, we changed the degrees to 72 and we changed the repeat to 5. We changed the angle to 90 and 4 to do a square, and to do a triangle, it was 120 and 3 is the repeats. And if we were in a class, I would actually have everybody tell me were the shapes they drew, how many sides their shape had, and what angle they had to use to bring and close that shape up. And if we start looking at it, we can see that there's actually a pattern here. And just to help with that, if we look at 3 and 120, and we multiply those together, we get 360. If we do 4 sides, and those are 90, and we do the multiplication there, we get 360. And if we do 5 and 72, again, we get 360. And if you haven't really introduced multiplication yet, we can say, oh, well, our angle is 120, and we have 3 of those. So we can actually do this with addition as well, which, of course, is the definition of the math. But we could actually do the sum of the 3 sides of 120 and see that that comes out to be 360. So there's lots of different ways we can manipulate and work with this in a very concrete way. Now, for those of you that have really spent some time in geometry, you know that the sum of all the interior angles of a shape adds up to 360. So you already had this kind of float in the back of your head, and you may have even not needed this table to see that. But the tables can be an extremely useful teaching tool to help the students really see a concrete connection between the details of these programs. So with that in mind, let's modify this program so that we can draw any arbitrary sized number of sides polygon, regular polygon. So to do this, I'm going to introduce a couple new blocks out of this sensing palette. And the sensing blocks have to do with how the sprite understands its environment. So it basically senses parts of the stage and information like that. But what we're really after is these 2 blocks, this ask block and this answer block. And the ask block allows the sprite to ask a question. In this case, what's your name? And if I would click that, it will show you the interface. So this is how we get input into our program. The turtle's asking me what my name is, and I can tell it, well, my name is Nathan. And I click the OK there or hit the enter, and that box goes away. But after that point, this answer block, which we haven't used a block in this shape yet, this shape is with the rounded corners. It really looks like kind of where we're typing in values here, and that's very intentional. This is what we call a reporter block. If I were to click on it, it would tell me that the value it represents is Nathan. So that was the answer I just gave it, and it holds on to that answer until we use the ask block again and get a different answer. So this can actually be dropped into a socket like the repeat to use that value for, instead of typing in a value, to just use the value that was a previous answer. So if we go ahead and put our ask up here, and instead of asking what our name is, ask how many sides do we want to draw, we can run this and it'll ask us how many sides we want to draw. Well, let's do 4. And we'll see that we still get a triangle, which you might be wondering about. But notice our turtle is now in a new spot. So it's actually drawn 1, 2, 3, and a 4th side. It actually went through an extra time because it drew 4 sides instead of 3. Now, this turn 120 degrees, we need to change that to be the angle that we need. And if you remember what we just talked about with that table, is that the number of sides times the angle is going to be 360. We can reverse that equation and say the angle we need is going to be 360 divided by the number of sides. And this is a chance to introduce another block. In the operators block, we have a division operation. So we can just pull this out and drop it in there for our turn and say that we want to take 360 degrees and divide it by the angle that we supplied. So if we go back to our sensing, we can pull out another copy of the answer block and drop it in that other socket. So now let's try drawing a four-sided shape. And we have our rectangle. If we do a nine-sided shape, so dodecagon, oh, something unusual happened here. It looked like it was starting off very well, but then we got to the edge of the stage and something weird happened. And I'll explain what actually happened is our sprites are not allowed to move off the stage. So at that point, while it was trying to still go up and to the left, it kind of just skidded along the side here, and then when it could move again, the shape no longer lined up. If we were to take and push this where the turtle currently is and push this line up with it, it would actually line up and make a nine-sided shape. So this is the other thing you can run into your students. Yeah, once they start doing something like this, every student immediately wants to do, oh, I want to do a lot of sides. And you'll see that doesn't really work because we get stuck in the corner there. So to fix that, the other thing we'll do is we'll modify how many steps we're taking. And it really doesn't matter how many steps they actually take, but we're going to basically do the same thing in terms of we're going to divide it by the answer so that as the number of the number of sides on our shape gets bigger, the distance those sides are drawn gets smaller, so it can just all stay on the stage. And we were using 100 for the sides on the triangle, which had 3 sides, so we could plug in 300 divided by 3 if we're doing a triangle. That should get us back to the size of the triangle, and then all of our other shapes should stay about the same size as that first triangle. So let's try that, see what a triangle looks like at that point. Boom, we have a triangle. Beautiful. If we go ahead and set it up to be 10 sides now, we get a 10-sided shape. And if a student wants to throw in a ridiculous number of sides, say 1,000 sides, it's going to take a minute. But if we're patient, we'll see it actually draws a 1,000-sided shape. And as you're watching this, notice that the distance between the sides is so small, so infinitesimal, that we're actually getting what appears to be a very smooth circle. And this is actually how computers draw circles. They do it with very small segments all the way around. And mathematically speaking, this idea of taking very, very, very small steps and moving around is essentially the foundations of calculus. So at this point, we have actually done some foundational calculus work at an elementary school level, and we've done it in a very concrete way. So students grasping this idea can help set the stage for later learning in math and give them a very concrete understanding of some things that are actually pretty hard to teach in the abstract. But if we can make it concrete, we can really make it approachable, and we can help students that otherwise might really find themselves struggling in later math classes really understand what they're doing. So this is an extremely powerful teaching technique, and I would encourage you to really think about how you can integrate stuff like this into your classes. And if you want to learn more about some of the ideas around teaching using turtle graphics and programming at that level, I'd highly recommend Seymour Paperin's book, The Children's Machine, where he actually really talks about kind of some learning theories that he developed through his efforts of doing outreach with students with the Logo programming language, which is obviously a big influence on Scratch, along with Smalltalk and a few other programming languages. But there are some really great things to garner there. And the Scratch programming environment with the block-based programming really makes that a whole level more approachable than the early programming languages like Logo. So this is, again, a really great teaching tool, and I'd encourage you to really dig in and see how you can use it in your classes.